I often hear creationists object to the Big Bang on the grounds that it violates the conservation of energy. Well, you see before you the two Friedman equations for what is known as perfect fluid cosmology, as well as several of their solutions for a flat space. Now, the Friedman perfect fluid cosmologies are derived from the general Einstein field equation. And the Einstein field equation has built within it the vanishing of the covariant divergence of the stress-energy tensor. In other words, built right into general relativity itself is the conservation of energy and momentum. Therefore, all solutions to the Einstein field equations automatically conserve energy and momentum. Now, what does the conservation of energy even mean to begin with? Creationists often phrase it as saying you can't get something for nothing. Well, that's not quite what the conservation of energy actually says. What it actually says is that a closed system maintains a net energy which is constant in time. That doesn't mean that there can't be changes in the local energy in one region of the closed system, nor does it mean that you can't add energy to the system while it's still closed. It just means that the net energy of the system remains closed. In other words, you can add energy to the system, but you would also have to simultaneously add an equal amount of negative energy to the system at the same time. An example of something which possesses negative energy is gravitational fields. And of course, general relativity often deals with the phenomenon of gravitation. The Friedman equations automatically, as long as this kappa parameter in the first equation, as long as that is zero, the Friedman equations automatically have a net energy of zero. What is that kappa parameter? Well, that corresponds to the net curvature of space. Not the curvature of space-time, the curvature of space. If it is zero, the universe is a flat three-dimensional space. If it is positive, the universe is analogous to the surface of a sphere, except it would be the three-dimensional analog to the more common two-dimensional surface. And if the curvature is negative, in other words, if the kappa parameter is less than zero, that corresponds to a universe which is analogous to a hyperboloid, only three-dimensional. Now, if the universe has a kappa parameter which is zero, that means that the net energy of the universe is exactly zero. That means that prior to the Big Bang, there did not need to be any energy added to begin with. In other words, a simple quantum fluctuation in vacuum could have easily produced our universe. Of course, this only applies if the universe is flat. Fortunately, recent cosmological observations of the size of regions of constancy in the cosmic microwave background radiation reveal that in fact the universe is flat, or at least incredibly close to flat. If there is any net energy in the universe, it is extremely small. However, it seems most likely that there is no net energy whatsoever. This, of course, as I said, means that the universe has no net energy. And it means, once again, that there did not need to be any energy added in order for the Big Bang to happen. If the curvature were positive or negative, you would have to explain where that extra energy or missing energy comes from. However, it isn't. Recent cosmological observations, one is known as the boomerang experiment, have demonstrated the universe to be, on the whole, flat. And these three solutions here, the radiation-dominated, matter-dominated, and dark energy-dominated cosmologies, are themselves examples of flat solutions. They themselves conserve energy, and they have net energy 0. You notice that the first two solutions go to 0 when t equals 0. The third solution does not. However, we know that initially the universe was radiation dominated, not dark energy dominated. The universe in its present state is dark energy dominated, which means it expands exponentially. However, that's the present state of the universe, not the past state of the universe. What does this tell us? This tells us that A was equal to 0 when t equaled 0. Now, what is A? A essentially is a parameter that has to do with the size of space itself. It's called a scale factor, and if you want to get technical, it's a factor that's on the spatial components of the metric tensor. But basically, in general, what it kind of means is a measure of the distance between points. So the larger A is, the larger the universe is. So, I don't want any creationists to see this video and come away still claiming that there are conservation of energy problems with the Big Bang. That would indicate that you didn't even listen to what I just said. There are no conservation of energy problems with the Big Bang. This is a mathematical demonstration of that fact. Stop using this something from nothing argument. It shows that you don't even know the basics of what you're talking about. If you want to refute modern cosmology, you're going to need to do a lot more work than just sit around and come up with clever one-liners.